Alright, Math 8 students, what we are going to do today is the Module 6 review, the Ready to Go On. We're just going to go through this real quick, and this is just for those of you who maybe want to get answers on a couple of specific questions in this review, or you just want to have a guided walkthrough of the review, or you're using it as an answer key. Again, this video is not required. It's just here to help you in case you need it. So in this module we are looking at functions, and in 6.1 we are identifying and representing functions, and there's 4 different ways that we usually do that. So what we've got here in our 6.1 in 1, 2, and 3 is that we've got a mapping diagram, we've got a table, and we've got ordered pairs. The other representation that we usually see a function in is a graph, but we've got that down here. So all we're doing in this one is that we are looking at to determine whether the relationship is a function or not. And remember that it has to be a function, each input should have only one output. And so that's what we're looking at here. We're just going to go through and look at the input of each of these, and looking at number 1, input of 2 has 1 output, input of 5 has 2 outputs, and input of 8 has 1. So right here, the fact that 5 has an output of 2 and an output of 1 means it is not a function. Now you can have outputs with multiple inputs, but each input should have only 1 output. Okay, so number 1 is not a function. Number 2, we're looking at our x values, seeing if they repeat, right? Because we're seeing if we've got any multiple inputs that have different outputs. And right now we can see that each input does not repeat, and it has only 1 output. So even though these share, 3 and 6 both share 5 as an output, that's okay because 6 has an output of 5 and nothing else, and 3 has an output of 5 and nothing else. So that means that it is a function. And then this last one that we're looking at here is a set of ordered pairs. And so just like our table, we're going to go ahead and check first for repeating inputs. So 2, 7, -3, 2, and 1. So we've got a repeating input of 2, and we're looking to see if this repeating input of 2 has the same output or different outputs. And in this case, 2 is matched with 5 and 9. So this input of 2 has multiple outputs, which means it is not a function. If 2 had repeated with the same output, that would be okay, but since 2 repeated with a different output, it is not a function. Alright, so that's identifying and representing functions. You'd also have a graph, and the thing to remember with a graph that you can always use is the vertical line test. And remember, that's just drawing a vertical line through any point on the graph and seeing if it crosses more than one point. If it crosses more than one point, it fails the vertical line test and it is not a function. I'll just give you an example over here. So if I've got a graph here, and I'll just do another graph here, and I've got this line here, and then I've got this one here. Okay. If I was to do a vertical line test on this one, it passes. And I could do that vertical line test anywhere. And it's only crossing once, so this would be a function. As opposed to this here, this is a function, but it's not a linear function, right? So it doesn't pass the vertical line test, which means it is not, this is not a function. It's not linear, it's not a function, it does not pass the vertical line test. You might have a function that is nonlinear, that looks like this, right? This is nonlinear, but it is a function. It passes the vertical line test. So, not a function, and this one is a function, just for some extra examples there. Okay, moving on to 6.2, describing functions. And we're going to determine if each function is linear or nonlinear and proportional or non-proportional. So what we're doing with an equation is we want to determine if we can put it into y equals mx plus b form, right? If it's linear, we can put it in y mx form or y equals mx plus b. Remember, that's called slope-intercept form, and this is slope form with a constant rate of change and a y-intercept. So Joan is paid $14 per hour. If we were to put this into an equation, it would be y equals 14x. So she is paid $14, where x is the hours and y is the amount paid. So that is a function. And since I can put it in this form, it's also linear. Okay? And since it has no y-intercept, it is proportional. This is linear and proportional. And then I'm going to go ahead and take a look at this next one, 5. And I'm looking to see if it's linear. Remember, if it's linear, I should be able to put it in one of these two formats. I should have a constant rate of change, and maybe I might have a y-intercept. So Alberto started out bench pressing 50 pounds, then added 5 pounds per week. So he has an initial value of 50 pounds, and then he's got a rate of change of 5 pounds per week. So I could write this as an equation in y equals mx plus b form. It would be my rate of change, or my slope, would be y equals, my slope is 5 pounds per week, where x represents the number of weeks. My computer's being slow. And I have an initial value of 50 pounds, so I would have a plus 50. Starts at 50 pounds, adds 5 pounds per week, and then that output would be how much he is bench pressing, right? X represents weeks. So since I can put this in y equals mx plus b form, it is linear. But since it has a y-intercept, it is non-proportional. Now, if it doesn't have a constant rate of change, if you cannot put it into slope form or slope-intercept form, it is not linear. If it is not linear, it is not proportional. Just like we were talking about this here, this is a function right here. It's a function, but it is non-linear. So that might be an example of that. And we know it's a function because it passes the vertical line test. Okay, moving on to 6.3. We're comparing functions. So which function is changing more quickly? And explain. So what we're looking at when we're comparing functions is we're generally looking at the rate of change, or slope, and the y-intercept. And those are two things that we'll look at and compare. So I'm going to go ahead and see if I can find the slope on this graph first. I know it's got a y-intercept of 20. But it wants to know which is changing more quickly, so that's actually not relevant in this case. But it gives me a point here, right? So this is x is 0, y is 20. And then I'm going to go, this looks like a nice clear intersection point down to here, which is 2 and 12. And I'm going to find my rise over run. I'm going to find my rate of change. So I'm going to go down from 20 to 12, which is 8, right? So that would be negative 8. I'll do this right here. And I go over 2, so that would be 2. I can simplify this to negative 4 over 1, or just simplifies to 4. So my rate of change for function 1, which is my graph, is 4. So function 1 m equals negative 4. And then I'm going to look at my rate of change for my second function so I can compare. So I'm looking at my change in x here, which looks like a plus 1, and then a plus 1. So my change in x is plus 1. And then my change in y, so I go from 11 to 6.5, which would be what? Negative, right? Negative 4.5. And then from 6.5 to 2 would be minus 4.5 again. So my change in y, or my rise, is negative 4.5. So this means that my rise over run, or my slope in this case, is negative 4.5 over 1. It simplifies to negative 4.5. So I've got negative 4.5, so function 2 m equals negative 4.5. So which one is changing more quickly? Well, function 2 has a rate of change that is greater than function 1. So function 2 is changing more quickly. And to explain, because it does ask us to explain, they're both negative here, so what we've got is function 2 has a greater rate of change, and I'm just do that the absolute value, right, of 4.5 is greater than the absolute value of 4. And I use absolute value because they're negative, and it's I'm just comparing the actual rate of change, so slope there. So function 2 has a greater rate of change because negative 4.5, or the absolute value of negative 4.5, which is 4.5, is greater than the absolute value of 4, which is 4. And I just use absolute value because I'm comparing the slopes. All right, and so the last question that we've got here is we are looking at our essential question: how to use functions to solve real-world problems. So functions are pretty neat. They're just like linear equations. You can use them to solve real-world problems because you can you can create a situation with an initial value, right, and then a rate of change. So if you're looking at like payment plans, or if you're looking at like a road trip where you have a starting distance and you're traveling so fast per hour, then it gives you that kind of stuff. So we're going to give kind of a general description here and say that you can use functions to find an unknown value or to predict a value, right? Use functions to find a value, an unknown value, or to predict a value. And the bottom line, the reason that you can do that is because functions means that there is a rule that is followed, right? And so that you're going to be able to predict that because each input goes through the rule and has a predictable output, right? So if you know your input and you know your rule, and you can usually figure that out, right? You know your rule, then you have a predictable output. So that lets us solve real-world situations. Okay, so that is all that we've got for this review. You might have done it on your own and not had any issues at all. If you just wanted a little bit of extra review, this is here to help you. If you want to use it as an answer key, you can use it that way too. There's, of course, some of these have more than one way to solve, but we are testing on this tomorrow, so if you have questions, please come with questions, ask questions, and get those problems solved. And I will see you guys on the flip side.